Hi, my name is Ding Li. I am a Senior Power Applications Engineer at Linear Technology. I'm going to talk about the LTC3871, a new bidirectional synchronous buck or boost controller to step down or step up the voltage between two voltage rails, such as the 48-volt and 12-volt batteries in dual battery automotive applications. This simple schematic shows basic functions of the LTC3871 supply. In buck mode, energy is transferred from the 48-volt battery to the 12-volt battery. In boost mode, energy is transferred from 12-volt to the 48-volt. An external signal controls the LTC3871 to operate in either buck or boost mode. The LTC3871 is a 100-volt and 30-volt bidirectional two-phase synchronous buck or boost controller. It operates in buck mode or in boost mode. Either mode is configured on demand with an applied control signal. There are 4 control loops, 2 for current and 2 for voltage, enabling control of voltage and current on either the 48-volt or 12-volt outputs. The integrated gate driver voltage is adjustable from 6 to 10 volts, which is ideal to optimize the overall converter efficiency. Up to 12 interleaved phases can be easily paralleled with excellent current sharing for high-power applications over 3 kW. This slide shows a simplified block diagram of the LTC3871, an output voltage loop and an output current loop. When charging a battery, the current loop makes the supply a constant current source first, controlled by the set current pin signal. As soon as the battery is close to be fully charged and its voltage reaches the flow voltage, the voltage regulation loop takes over to maintain the flow voltage. The LTC3871 can be dynamically and seamlessly switched from buck mode to boost mode and vice versa via the buck pin. There are 2 separate error amplifiers for V-high or V-low regulation. Having 2 error amplifiers allows fine-tuning of the loop compensation for the buck and boost modes independently to optimize transient response. Resetting soft start and parking the ITH pin at the 0 current level ensures a smooth transition to the newly selected mode. From the waveform, you can see that the converter settles within a few switching cycles during the buck to boost transition. The inductor current and V-high and V-low voltage are well controlled during this transition. In order to mimic the dual battery system on the bench, a 60-volt 5-farad equivalent supercap bank is connected to the 48-volt side, and on the 12-volt side is a bipolar power supply that can source and sink current. Let's set the LTC3871 to boost mode first. When I power on the 12-volt power supply, the supercap bank is charged to around 12 volt through the body diode of the top MOSFETs. Now, let me turn on the board by releasing the run jumper. It is easy to adjust the LTC3871 charging current by changing the set current voltage. You can see that the V-high voltage is ramping up. The charging current is proportional at the set current voltage. When the V-high reaches its regulation point, which is 48 volt in this case, the LTC3871 naturally transits from constant current mode to constant voltage mode. When I toggle the switch to buck position, the LTC3871 enters the buck mode. Supercap starts to discharge. Now V-high falls below 30 volt, which is the undervoltage threshold. The LTC3871 stops switching. I am enabling an external load to help the supercap to discharge faster. Now, let's demo the dynamic buck boost mode transition. First, I have to toggle the buck boost switch to the middle position. Then, I attach a 2 Hz PWM signal to the buck boost turret. Now, let's look at the waveforms of buck boost, set current pins, V-high, and inductor current. when the mode changes from boost to buck and the set current voltage changes its value accordingly, the inductor current smoothly changes its direction. Meanwhile, the V high drops because current flows through the series 0.1 ohm resistor. For a high reliability automotive application, we need a multi-phase supply to operate with phase redundancy. That is to say, the supply can continuously operate even if one phase fails. The LTC3871 can work with the LTC4368-1 for phase failure protection. At fault, usually overcurrent, overvoltage, or undervoltage is detected. The LTC4368-1 disconnects the failed phase and pulls the LTC3871 OV high pin high. Then the particular LTC3871 will stop switching and disconnect its related signal pins from other controllers. The remaining LTC3871 ICs will continue working without any interruption to input and output rails. The LTC3871 can be easily configured as a polyphase converter to support higher power. Here is a board of a 12-phase 2.5 kilowatt converter. The full load efficiency is over 97.5%. The LTC3871 employs a unique current sensing architecture and can operate reliably with a small current sense signal of a very low value inductor DCR or R-sense to improve power efficiency. Meanwhile, excellent current sharing can be achieved because of the low current comparator offsets. In conclusion, the LTC3871 is an efficient 100-volt DC bidirectional buck or boost controller that supports CC/CV battery charging. Its unique architecture allows quick and smooth buck-boost mode transition. IMON and set current pins allow precise current monitoring and programming. LTC3871 IC supports polyphase for high power. Up to 12 phases can be paralleled and clocked out of phase for high current applications. It can be used in a dual battery system as well as other applications that requires bidirectional energy transfer. Visit us at linear.com for more information. Thank you.